Is that good? Use your calculator to begin this course. I'll get you the forms to sign everything later. Yeah, okay. So we have one more. I just want to show you if you had, 1/3 x minus 4 squared, something like that. We know it's a quadratic, but we're looking at the leading coefficient, which is 1/3. All of these would be considered wide, like they would be wider than normal. Okay, they would open up. It will help us to find our window. Okay, and so we'll do some examples here. And I also want you to see just weird setups. Right? It's like, okay, it can look like this, right? And don't be scared. You can type that into your calculator exactly the way it is. Okay, exactly this way, using brackets and everything, and it will graph it for you. So I can scare you with interesting equations, right? Y is equal to x squared. F of x is equal to x squared plus 1. Y is equal to x squared plus 3x plus 4. F of x is equal to x minus 1 squared minus 7. All of these have a leading coefficient of 1. Every single one of those. Okay, and the last one, f of x is equal to 3x squared. Y is equal to 5x squared minus 1. F of x is equal to 7x squared plus 5x. Y is equal to 4.5 x plus 7 squared, and just leave it at that. Now, can we just, I'm just going to add a couple negatives here. So let's make this one here a negative. And let's make that last one here a negative as well. Because right now, when you're looking at the width of the parabola, all you care about is the actual value of A, the numerical value. Is it bigger than 1? And it is, right? Even here, the 4.5. It could also be a fraction, right? It could be 9/2, right? 9/2 is 4.5. But if the numerical value is greater than 1, it's a narrow parabola. Okay? And here is where the calculator is going to come in handy to show that. Okay, so let's grab our calculator for one moment here. Let's go to y equals, and let's clear everything that's there. Just go arrow up and down, make sure everything is cleared. Go to the very first one. Let's type in 0.85 or 0.85 if you like, x squared. Okay. And let's go ahead and graph that. We know two things. It's positive, right? So which way is it going to open up? It's going to open up, right? I already gave it away. Right? It's going to open up. and it's going to be wide because the value is between 0 and 1. Okay, so that's graph. There it is. You're like, I don't know, kind of looks normal to me, right? Well, let's see. Now we're going to go back to y equals. And for y2, we're just going to enter x squared, right? 1x squared if you want to look at it that way. And let's hit graph. And it's hard to see, but you can tell that the red one is slightly narrower, right? You see that? Or if you don't see it, press zoom 6. Press zoom 6 if you don't see it. Then you'll see exactly my screen. Let's increase our Y max to see more above, right? So we're going to go to window, Y max. I'm going to go to 50 there. Y max, I'm only changing my Y max to 50. Then hit graph again. It's a little bit more visible, right? The difference, right? The between the two lines. So the wide one, and then there's a normal, and let's go ahead to y equals. Let's type in 3x squared for the third equation, 3x squared, like that, and hit graph. And the third one comes in, which you can tell is narrower. Do you see that? Yeah. So it actually, right, you can visually see that that's the case, right? You can kind of look at it this way: the bigger your value, the narrower it will become. And if the value gets smaller, it will open up, right? So that's kind of how you want to look at it. Okay, let's keep going. So more examples here, and I'll just give you some variations here. So y is equal to x squared minus 3. Then you're going to have f of x is equal to negative 2x squared plus 3x. And you're going to have y is equal to a quarter x squared plus 3x minus 7. So I'm giving you some examples, right? So I want you to tell me for every single one, we're going to walk through it, what's the width of it? And what is the opening? Okay, so the width and opening for all these equations here that we just saw. Okay. And I'm just going to identify, so write them down first. And then we're going to find A for all of them. Okay. A for this first one is equal to 1, positive 1 that is. Okay, I'm going to put a positive 1, so it's right here. This would be, the width would be considered normal. Why? Because A is exactly equal to 1. And the opening is up. And why is that? A is positive. Right? So it tells us two things. For the second one, A is equal to negative 2. So we know that this one is going to be narrow because that's supposed to be an O there, because A is bigger than 1 and it's going to be pointing down, right? Because A is negative. So we're looking at the sign for this and we're looking at the numerical value for the width. Okay. Here A is equal to a quarter, positive that is. That would result in a wide parabola because A is between 0 and 1. And it would be opening up because A is positive. So that's, I hope that's kind of sinking in now. Okay. And I see a lot of you are taking advantage of the video, so that is good, right? Like you're actually trying to see, have a second look at it, right? Okay, the third characteristic is the vertex. Vertex, okay? That is very important for us. You will see that as we do more problems. It is the coordinate in the form xy, comma, where the parabola changes direction. It could be at the peak or valley, right? Depending on its opening, it will be referred, to as, I don't know if you recognize the second trace I told you later, right? Min, right? Or max. When using the calculator. So when the parabola is opening downward, right? You have, if you look from the left to right, it's going to be graphed this way. It reaches the highest point and then it changes direction. It goes back down. So that is what we call the vertex. So in this case, it would be a max, right? The highest, right? And if it opens like this, that would be a peak, right? The peak or the valley, that would be your min. Okay. And I will just say here, both min and max are called vertex. Okay, so don't think that one is different than the other. They're both. It's just that if you want the vertex in this case, you'd have to use the min. If you want to find the vertex for this parabola, you'd have to use the max. Okay. And I will add something once you've this space right here or somewhere. If you have the space, I'll just tell you use second trace min or max, right? Like to access the vertex, you're going to have to use second trace always. Whenever you want to find something about the graph, you go second trace, and then it's either min or max to get there. I will show you how to use that later on, okay? And if you're taking physics this semester or last semester, you will see some correlation there. Projectile motion, right? Like how things fly when you throw them up in the air. That's where we're going. So you're going to be like, oh, I didn't know that there was an overlap, right? So there's a bit of an overlap there. Except for you get to use your TI-83 for it. 84, sorry. 83s are old. So you have the privilege of using nice color screens calculators. Okay. 4. This is what we call the axes of symmetry. And symmetry is key for, I will tell you how I'm going to refer to it, axis of symmetry, because it just gets too tedious to write it out every time, is the vertical line that cuts, right, cuts the parabola into two symmetrical halves. It is always a vertical line and it is stated as an equation, and it will be x is equal to the x value of vertex. And this I'm going to box in. Since it's a vertical line, if you recall, x equaling a number is a vertical line, right? So the axis of symmetry you should think of as a line, so it's always stated as x is equal to a number, and I'll tell you where to get that number from. So let's do a sketch here. X and y axis. And I want you to go, let's pretend this is 2, 3 up here. It's 2, 3, just roughly, okay? And I'm going to show you a trick on how to draw nice parabolas. This is what is going to be my vertex. And so you don't want to go out like a V or something like that. You kind of want to go out to the side a bit and then kind of curve downwards like that. And then try to mimic the same thing, because this is the vertex is the middle. And then from there you move out. Try to keep the same distance and move down like that. If it doesn't look perfect, it's not the end of the world. We're going to get better at it. Okay. So if this is a parabola, if they talked about the axis of symmetry, it would go down right through the vertex. So I'm going to make a dashed line here, right? That is the vertex. Sorry, the axis of symmetry going through the vertex. And that equation of that line would be x is equal to, what's the x value of the vertex? Because this is the vertex up here, right? The coordinates of the vertex is given by 2, 3, correct? So the x value of the vertex would be 2. That's what you put down here. Okay. And I'll write it one more time on the side here. The axis of symmetry. So you're saying this is what it is. It's x is equal to 2. And I'm going to draw a line from the vertex, the coordinates of the vertex. And it's going to go all the way over, and it's going to go down to where I placed it to, because that's where I got it from. Okay. And I'll say it because it happens too often. Not a point. It's a line. Okay. It's that line that cuts this into two symmetrical halves, right? If you were to fold it along that axis of symmetry, they should, this arm and this arm should perfectly line up. Okay, so that is the axis of symmetry. And this is what we call the vertex. It's the actual point. So that's how they're different, okay? I'm going to try to leave it right there in case somebody's still doing that part. Number 5. And this is where it gets a little, the wording is key here. If the parabola opens up, it has a minimum okay. If the parabola opens down, it has a maximum. Didn't he just say that? Well, I talked about the vertex, and if you want to use your calculator to find the min and max, you have to use min and max there on the calculator. But if I ask you write the minimum or the maximum, this is what I'm asking you to do. It is also a horizontal line written as y is equal to the y value of the vertex. Using the graph above, the equation of the, in this case we had a max, right? If you look at up here, of the max is y is equal to the y value of the vertex above was 3. Okay, so there it is. So you get the axis of symmetry from the x value, and you get the min or the max. There's only one. A parabola cannot have a min and a max. Okay, so it depends on, right? If this had been pointing up, if you wanted me to give you an example of everything, we would be taking notes until July, right? I can't do that. Nobody wants to sit here in July, so I'm just giving you an example, and this is what it would be. And I'm just gonna maybe highlight max, right? If it had been pointing upwards, it would have had a min, right? Then the equation of the min is y equals 3 if this had been pointing up, right? So just be careful with that. 6, x-intercepts A parabola quadratic can have 0, 1, or 2 x-intercepts. Interesting, right? So far linear, right? Linear could have one only, but quadratic can have 0, 1, or 2. By the way, the power of the function, the power of quadratic is 2, right? That's like the maximum x-intercepts you're going to have. Next year, you're going to have a power of 3, right? You will have a maximum of 3 x-intercepts, okay? So I'm going to give you some graphs here, just to give you some. So 0 x-intercepts is when you have the following situation, okay? So let's just do this first, set it up, and then I will give you the actual graph. 1 x-intercept, just have a small grid there, doesn't have to be fancy. And then 2 x-intercepts. I'm going to write stuff under these graphs yet, so if you don't have room, just continue on the next page, right? I'm going to try to keep it short. So 0 x-intercepts, these are just some examples. So let's say our vertex is here, and it is pointing up from there, right? That would result in no x-intercepts whatsoever. Same thing for pointing down. So we're just going to do the same thing over here on quadrant 4 and just go out from that point. And we have arrowheads for now because we don't have a restriction, right? So it just continues. Then you have 1 x-intercept. That's when you end up having your vertex right on the x-intercept, right? So let's do one on either side. Let's make this one point up. So I'm going to go this way, and I'm going to go this way, right? And this one is going to be going down. Let's make this a little narrower because they will vary in the way they look, right? So the vertex is right on the x-intercept. Okay. 2 x-intercepts. You can probably guess what's going to happen. The vertex is going to be here, and I'm going to be going upwards and upwards. And then you're going to have an x-intercept here, for example. Let's make that a little narrower. You're going to go this way and this way. Okay. And I'm going to, for this last one, I'm going to actually highlight the fact, right, it crosses here and it crosses there, crosses here. So in these two graphs, you end up with 2 x-intercepts. 1 x-intercept, no x-intercept, right? So I'm going to add a few things here. And it all has to do with the vertex combined with the opening, right? Which way is it opening, right? So those two things you're looking for. So here, vertex above x-axis and a positive. So I know it's a little small, folks. I apologize. So vertex is above the x-axis and a is positive, then it points up. And the second case here, vertex below x-axis, A is negative. So those are the two scenarios where you would have no x-intercepts. Second scenario is less work. Vertex is on the x-axis. A can be positive or negative. And then the last one, let's just see, right? Vertex below x-axis. A is positive, okay? Or vertex above x-axis, and A is negative. So you can kind of try to, after today, look through these notes and internalize this, right? But if the vertex is below and A is positive, obviously it's going to cross twice, right? Because it always has two legs. It's the vertex and two legs, right? Doesn't matter which way it's pointing, always has two legs. Okay. I really would like to get to graphing quadratics, but we'll see how it goes. Can you see back row, especially when I write small? Yeah. Can you see? Yeah. Okay. All right. Number 7. There's 8 in total, by the way, if you're wondering when is this ending. Domain and range. This is huge. Not just this year, next year. Okay. And not just in this unit, it'll be in other one more unit as well. So domain and range. Right? The domain have a quadratic is D, right? Domain is usually X. Watch this wording. X is part of or belongs to, so it's like an E like this, all real numbers. So basically all X values go, or negative infinity to positive infinity if you want to use set notation, and it has to be round brackets on both sides. And this is a big, this changes, okay? This changes with word problems. That's very important. I should not be seeing infinities with word problems, okay? Oh, it's supposed to be a star here. Okay, this changes with word problems, so be careful there. So if it's just you're looking at a parabola, right? No word problem attached to it whatsoever. It's just x and y. Then your domain is either this or this, depending on what notation you want to use. And this is just x belongs to all real numbers. That's just saying that there's no limit, okay? Because it opens up to the sides indefinitely, right? So all x values are acceptable. A range. If it opens up, right, your range will be different. That's not, so it'll be either y is greater than the minimum, or min to infinity. Opens down. If it opens down, y is going to be less than or equal to the max, squiggly brackets, or -3. Oop, no, sorry. I'm looking at the example already. There's no example here yet. Or -infinity to the highest value, which is your max, and it will usually include it. Okay. We don't really have open dots in Parab when it comes to this, so that's what it is. Examples. So for range, you should have this on your study sheet, right? Domain and range is going to be huge. Yeah, go ahead. So examples here. I'm going to make a grid here and we're going to graph one, just sketching it really. So no need to put a scale on these ones, okay? I hope that is clear that it's just because it's for illustration purposes. So let's say we have a point somewhere over here. So put it down here and it's going to be opening up. So -5, -3 is our vertex. Okay, and from there I'm just going to go up like this. And I'm going to do the same thing here. Okay, and so let's say I would ask you for domain and range on this one. And we're going to call this x and y, of course. So if I asked you for this, for domain and range, it very much revolves around the vertex when it comes to the range. And it's domain, not so much, right? So for domain here, it just opens up indefinitely to left and right. So it's either this, whichever one you prefer, or -infinity to +infinity, round brackets on both sides. For the range, it's a little different. This here would be referred to as the min, right? It's still the vertex. That doesn't change, right? This point is considered the vertex, but it is the lowest. It's a minimum for us. So it'll be looking like this, right? So y is always going to be greater than or equal to the lowest value, which is -3. And this will require some practice, right? But it's the y value that you're looking for. That is your min, right? With our calculator, we would use the min to find it, but then the equation of the min, right? When I ask you to state the min, it's -3. That'll be a horizontal line going through there, okay? But that's the value you want for the range. So y is always bigger than -3, but never less. Or you use this format, right? You're going from -3, including, to positive infinity like that. One more example. And this time we're going to put the vertex here, going down this way, going down this way. Not the prettiest. We call the vertex 7, 4. And we're going to write down the domain and the range. In this case, my domain stays the same. These are the official squiggly brackets, okay? And for range, this is a max, right? That's the highest point I reach. So if you look up there, y is going to be less than, right? It's always going to be less than or equal to 4. Okay? Or it comes from negative infinity and stops at 4, including, okay? So always from the bottom up, right? It stops at 4 for the y value. Last characteristic is the y-intercept. A quadratic equation or function will only have one y-intercept. The constant c determines the y-intercept, or gives us the y-intercept. But I will give you a little. This only applies to the standard form of the quadratic. And right, by that, what I mean is it has to look like this. Right, it has to look like this. If you have any brackets or anything like that going on, that value that's tagging along at the end is not the constant. And we'll look at that a little bit more when we get there. Then you'll have to use your calculator for that one. So example, f of x is equal to negative 2x squared plus 3x minus 4. And so what I'm going to do here, pause for a moment. When you have something like this, I need you to be able to tell me what is A equal to, what is B equal to, and what is C equal to in this particular case. Using this format, right? A is always in front of x squared, so it is negative 2. It's not negative 2x squared. It is just, A is just talking about the value in front, so it's negative 2. B is positive 3. C is negative 4. Okay. And it is this one, the y-intercept is 0, C in general when it's in standard form like this. Therefore, y-intercept is 0, -4. I'm going to try to get one more in here. Y is equal to 2/3 x squared minus 3x. If I asked you what's the y-intercept, in this case, there seems to be no C value there, but it is really 0. Okay? So it's really plus 0 there. So the y-intercept is 0, 0. Right? We've replaced C with whatever C value is in here, which is 0. So it's the origin. Okay? Now we're going to graph one. Finding the y-intercept with a calculator is done the same way as you've done so far. Second trace 1, x is equal to 0, and it will give you the y-intercept. So we'll do that just to make sure that, sometimes students need to see it. It's like, oh, okay, I see it. It's always this value at the end here. We can just get it from the equation, but sometimes you're going to have to use your calculator because it's not always going to look like this. As you've already seen, right? You've seen variations. I'm going to stop this recording here and just start a new one for